Now we also have committee size as input. Okay. Now the goal here is to find a committee of size k. Okay. So what should be my next question? Rules, right? So fine, I want to find a case size committee. Now what is my rule? Okay. Okay. So okay, there are a lot of rules, but I will tell you a family of rules. Okay. So this is called committee scoring rules. Okay. So in committee scoring rules, we define the satisfaction of every voter as a function that considers only the position of the committee. Okay. So can you relate it with yesterday's lecture? Yes. Huh? What do you mean by that? Mhm. Okay, so position maybe you want to say, right? Position of a voter in the ranking, right? You want to say something? Something like the border, right? Because border also consider the position of candidates in the ranking, right? Okay, so these are some named things, but of course you can imagine anything, right? Okay, so let's say this is my committee. Okay, now we will define something like position vector for a voter V. Okay, what do I mean by that? So position vector is defined for specifically for a voter and a committee. Okay, so let's say if I write, let's say this is my position vector. Let's say this. PV. Okay, so let's say I'm talking about the voter V1, right? Look at the voter V1. Look at the voter V1 and look at this committee. Okay, now look at these committee members in the, sorry, in the preference of this voter V1. Okay, okay, so what is its position? 1. What is its position? 2. What is its position? 3. Right, so position vector is the sorted vector of the committee members in the list of a voter. 1 and 3, sorry. Okay, is that clear? See, these definitions are going to be very important because the whole lecture is based on these things. So if you do not understand the definitions, please ask now. Otherwise, you'll be lost. Yeah, it has to be sorted. Okay. Okay. So sorted vector of the position of the candidates in the committee in the ranking of V. Okay. So similarly, we can define the position vector for every voter. Okay. So this is, let's say, position vector of V1, position vector of V2 is what? Tell me. 1, 2. Position vector of 3, V3? 2, 3. Okay. So I hope now everybody is clear what is the position vector. Okay. Okay. Now given this position vector, we will define the committing. Yes. Correct. No, this is any, I just chose any any two candidates. There's nothing late. I just chose any two candidates. Okay. So how to choose winning committee, that we will discuss later. But I just took an example to explain what do we mean by position vector. Okay. Okay. So now committee scoring function. So it's just a function which takes the position vector and return a score. Okay. So you can imagine this is like a function, right? Okay, should I write maybe a little big? This is a function, right? And because we are talking about k-sized committee. Values will be from 0 to m minus 1. Okay, it's position vector, sorry, 1 to m. Okay, and it will give you some score. Okay, for now I have written a real number. Okay, but in this talk we will just focus on natural numbers. Okay, could be anything, depends on you. Okay, so let's define two scoring rules. Okay, so the first scoring rule is best scoring function. Okay, so what will it do? It will take a position vector, right, and subtract the position. M is here total number of candidates. Okay, okay, okay. Let's take an example. Okay, so let's say this is my committee. Okay, and let's say my lambda is k, and k is what? 2 here. Okay, so lambda is also 2. Okay, okay. Let's say what is the scoring function for the voter V1. Okay, okay. So what is position vector? 1 3. Correct. And then what is the base value? M minus P1, which is what? 3 minus 1 plus 3 minus 3, right? So 2, right? So essentially what we are doing, we are assigning a score to every voter. Okay. You will also call it as a, let's say this is for voter V. Okay. So we will also call it as a satisfaction of voter V. Okay. And from, let's say, committee S. This is committee S. Okay. Okay. So what are you doing here? Let's see. For voter V1, if you want, so just project this committee on your preference list. Just focus there. Okay. Look at their positions. Okay. Subtract this from total number of candidates. Subtract this from total number of committee. Subtract everything for all the committee members. Right. Take their summation, and that is your satisfaction. Okay. Correct. Yeah. So, for example, I have taken lambda as 2 here, right? If you, let's say, take lambda is equal to 1. You can also take lambda equal to 1. Lambda is anything. It's given to you as part of input. It is anything less than equal to k. Okay. So, let's say lambda is 1. Okay. Then what will you do? Summation goes over 1 to lambda. Correct. So, what will you do? You will just do m minus p1. Right? So for voter V1, what is your satisfaction? 2. I mean, yeah, it happened in this example. Okay. Okay. But for example, if you see for V2, right? Then under lambda is equal to 1, it is what? It is 3, right? But if you look at the previous, sorry, here it is 2, right? But if lambda is equal to 2, then it will be 3, correct? So definition of best scoring function is clear? Yes, lambda is a fixed number. No, lambda is given to you as part of input. No, it's anything between 1 to k. It can be k by 2 also. No, it doesn't depend on ordering of committee. No, committee you have to choose. When you say ordering of the committee, that means you are talking about, let's say, 2, 3, 4 committees, and then you are talking about some committee. Committee is the unordered set. So, no, wait. This is ordered, okay? But committee is not ordered, okay? It is any set. It is an unordered set, right? Now you have 2 people, right? 2 candidates. right? Just look at their position in this ranking. It position vector is an ordered vector, but committee is set. Yes, absolutely. It's an order thing. Yes. No. No. So lambda does not have any relation with the ordering. Okay. So lambda is imagine that lambda is just an input. So in the input, what do you have? You have voters, you have candidates, you have rankings, you have k. Okay. When I'm talking about best scoring function, you also have lambda as input. Okay. So suppose you're saying this committee is one person. It doesn't matter. You put committee is unordered. Okay. So you put this. Okay. Now what will happen? You will again see this committee in the ranking of voters, right? It is going to be same. Position vector is still same. Right? You just look here. It is an unordered set. Okay. Okay. So is the rule clear now? Yes. Hmm? Okay. What would be? Okay. See, what will it be? Green and red, right? So it will be 2, 3. No, yes, it is same. Again, because the reason is for the committee, yes, committee is unordered. It's not an ordered set. Okay, it's going to be same. Yeah, but if you flip the blue and red guy, then it's going to change. Okay. Okay. Any other question? Okay. So let's look at one more rule. We'll just complete the definitions and then we will do algorithms today. Okay. So median scoring functions. Now you do not have summation here. Okay. So again, you have lambda as an input, right? Okay. What does it mean? It is basically saying in the position vector, I care about the lambdath position. Forget about everything else. Okay. That's the rule. Okay. So what we are saying, we are just saying m minus p lambda. Okay. Okay. So for example, let's say my lambda is 1. Okay. Okay. So if lambda is 1, then for voter V1, right? Position vector definition same. We are not changing that because if you notice, we are just changing the scoring function. Okay. Okay. So for voter V1, what is the position vector? It's same, right? 1, 3, right? My lambda is 1, right? So what will I do? M minus P1. Correct? M minus P1 V1, let's say. Correct? What is that? M minus 3 minus 1, which is 2. This is my P1, this is my P2. This is sorted thing. Right? So 3 minus 1, 2. Clear? Or confused? Already confused? It's fine? Okay. I didn't get you. I mean, the name is like a median. So you are saying why not at the center because the term is median. No, it's not like that. Then if you notice that median finding problem also is like one thing. Kth also we find. Kth largest also falls in that. So okay, but the name is like median. Okay. Okay. So both the definitions are clear, right? Okay. Now we know what is position vector. We know what is the scoring function. Now given this scoring function, we will define a voting rule. 2 voting rules actually. One is utilitarian. Okay. So what you do, I defined you scoring function, right? Using that, you can find the satisfaction of every voter, right? Given a committee, you find the satisfaction of every voter. Okay. In utilitarian type voting rules, whatever is your scoring function, you find the satisfaction of every voter and sum it up. Okay. So let's say S is my committee. Okay. So what is this? Summation V belongs to V. V is my capital V is my voter set, right? Satisfaction of, okay, okay, okay. So next type of rule is egalitarian rule. So here you try to maximize the least satisfaction of the voters. By satisfaction, I again mean the same thing. What you try to do here, you look at, let's say, okay. So look at the satisfaction of voters. Okay. Look at the minimum one. That is what you are trying to maximize. Because what are you trying to do actually in this rule? You are trying to make everybody as happy as possible. Right? This is more natural than utilitarian, but at some places utilitarian is desirable. In utilitarian, what is happening? Sum is maximized, right? So it is fine if someone is very happy and someone is like unhappy, right? So there we just care about the total satisfaction. But in egalitarian, we care about everybody actually. Like in here, I care about everybody. That everybody should understand. Okay, not like one person understand everything and someone doesn't understand anything. Okay. On what set we are taking minimum? So minimum is this, right? Sorry, sorry. This min is over, yeah. Min is V belongs to V. Okay, and this is the thing that you want to maximize. Okay. Okay. So, but in this talk, we will focus on these type of rules, utilitarian type of rules. Okay. Okay. So the first rule, this may sound familiar to you, okay? But I just said the generalized version of it. K-Boda. How many of you know this rule? Boda, I told you, right? Exactly. Okay. But I will tell you, actually, I just said these definitions only. Generalization of this. Okay. So what happens in K-Boda? It is a utilitarian type rule. Okay. And best scoring function with lambda is equal to K. Okay. This is my K-Boda rule. Is the definition clear or I can write again? That's fine. So what do we want to do? What is the objective? Function, summation, V belongs to V, right? And satisfaction of V. Okay, S is my committee. Right? And satisfaction, you know, I calculate using scoring function. Correct? Okay. So, and this is what we are trying to maximize. What do you think? Is it a polynomial time solvable problem? Okay, is the definition clear or should I explain using example? What do you want? Everybody? Definition is clear? Okay, good. Now, tell me. Whole problem. Compute, yeah, okay. Given a, this is a good question, right? Given exactly, given a committee, can I find the Moda score, right? It will be volatile. Do you know the algorithm? Oh, then why? How is it volatile? So if you do brute force, right? Let's say there are m candidates, right? So by brute force, do you mean you will try all possible sets? So how many sets are there? M choose k. Is it poly? But what is m choose k? Is it polytime? Polynomial number? For, yeah, of course. If k is constant, then yes. Right? But not in general. Input has k, yes. So, but k is not constant. Input also has n, input also has m. But is it polynomial in the input size? No, right? Just k is what, like m to the power k. Correct? So it's exponential. Is it polytime? Doesn't look like, right? Because we have to go over all. But the good news is it is polytime. Okay? So, uh, yeah, this is the definition. So let's try to understand the definition once again. Okay? So we had summation v belongs to v. Why is it always a problem for my talk? Oh, it was too long. Okay. Sorry. So summation v belongs to v. Okay. And then let's say S is my committee. Okay. So then what will I do? Summation I'm just writing both the summations. Okay. So summation I equal to 1 to k, right? And then m minus pi and v was here, right? Huh. So this is the thing, right? But if you notice, this is linear because of the linearity of summation. I can also do. Are you recording? Are you taking screenshots? Right? Yes. Right? I can do this, right? I can write it. Now it's very simple. For every candidate, let's compute the score like we did yesterday, right? Let's call that as beta. Beta C is what? Beta C is what? Summation V belongs to V, okay? M minus position of C in the preference list of voter B. Okay? Okay. So let's say if I want to compute beta score of this green. Okay. Then green is here, green is here, green is here, right? So M minus position, this is what? M minus 3 minus 1 plus 3 minus 1 plus 3 minus 2. 2 plus 2 plus 1, 5. Okay, this is how I can compute the beta value for every candidate. Okay. Now, top K. You can do without sorting. Okay. Think about it. This is an exercise. Without sorting, you can do. You need to remove this log K factor. Remove this log factor. Yes. You do this in order m time. M or mn is fine. M plus n, but remove this log factor. Okay, this is an exercise for all of you. And if you don't find, then Sumit will tell you. Yes, but now don't tell to everybody. Yeah, think about it. Let everybody think, because yeah, you all know this. Okay, you all have done some algorithm course, right? So you all know this. Just think in coffee break and just come out of that question. Now it's a polynomial time algorithm. Yes? Yeah, that's what I'm saying. Please don't tell it to everybody. Okay. So, yeah. So is the correctness clear to you or everybody? Why this is fine? I can take top K. Okay. So this is actually simple. You can think about it. If you don't understand, then you can come back, right? Just think that, okay, fine. If it is not, there is someone else whose score is large. Then where does it fit in my sorted list? For argument, you can use sorted list. Okay. Okay. So just think about it. It's simple. Okay. Okay. Now let's move to, oh, yeah, another rule. So this also I told you already. This is again a utilitarian rule with median scoring function lambda is equal to 1. Okay. We saw the example for lambda equal to 1 only. Right? Right? So what will we do here? Summation V belongs to V, right? And M minus P1 V. Correct? Okay. So again, do you want to see example? We already discussed actually this. So do you want to see the example or it is clear? Definition is clear? Okay. Because we will see a nice algorithm for this. So the definition should be clear to you. Okay. So what, okay, let's go over it again. So what are we trying to do here? Okay. So look at the, okay, this is your committee, right? Look at the topmost person in the in your ranking list, which is in the committee. This, for this also, this, okay, for everybody, unfortunately. Yeah. Okay, let's replace this red person with the blue person. Okay, that's a better example maybe. Okay. Now you see, earlier the difference was not clear actually. But now you see, huh? Okay. So now basically you need to subtract m minus 1 plus m, like 2 plus 2 plus 2. Okay. That is the score for this particular committee, right? And your goal is to maximize, find a committee which maximizes this score. Okay. Okay. What do you think? It is polytime or NP hard? Now, yeah, now you know what is NP hardness. So is it polytime or NP hard? Any guesses? NP hard? Yes, your guess is correct. It's NP hard. Okay. Okay. So we will not go too much into the correctness of NP hardness, but I will just give you a proof sketch. Okay. How can you, yeah, get it basically. Okay. So we can give a reduction from the vertex cover problem. Do you all know? Yes, you all know what is vertex cover problem. Right? You saw it yesterday, you saw it today. Okay. So you have graph G, vertex set and edge set, right? Okay. So let's go step by step. So for every edge, I will, okay, let's fix the notation. EUV. Okay. Okay. So for every edge, let's have a voter. Okay. So I have a voter, let's say EUV. Okay. And the endpoints of this edge, I will rank here. They get the topmost rank in any order. I don't care. Okay. Okay. After this, I will add the remaining vertices in any order. So basically, edges are mapped to the voters and vertices are mapped to the candidates. Okay. Okay. On purpose, I left this space. Okay. So this is how you have. Okay. No, vertex cover, we started with undirected graph. Ordering, so for this particular edge, U and V are the endpoints. Order, like you can choose any order, arbitrary order between them. Here, any order. Okay, think about these chunks, and this here in this chunk you can have any order, in this chunk you can have any order. Okay, I mainly care that this should be top 2. Okay. 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 So now what are we trying to capture here? That for every voter, right? Sorry, yeah. Yeah, for every voter, you pick something from here. I want to enforce this. If I enforce this, then do you agree that I will get a vertex cover? Right? Here in vertex cover, I am looking for a k-sized vertex cover, and that k and k is same. Okay. So here you have instance g comma k, right? And committee size is also k. Okay. So this is the goal. Do you all understand why am I doing this? Yes. How am I constructing graph? We are not constructing graph. Oh, our representation, we don't care. Why do you care adjacency list? Do you mean this matrix or list? What is GG? Is a graph? Hold on. He can speak, right? Let him speak. Have you seen NP hardness reductions? Anything. Take any instance of vertex cover. Do you know what is graph? Okay. So we are trying to show that CC is NP hard. Okay. So what will we do? We will start from a known NP hard problem and construct an instance of our problem. Right? So this known NP hard problem, I started with vertex cover problem. Okay. So what is the instance for vertex cover problem? A graph G and an integer K. Okay. And what is the question? Find a subset of vertices, right? Such that for every edge, at least one of the endpoint is in your set. Correct? This is the vertex cover problem. Okay. So you start with any graph and K. You start with any instance of vertex cover. It's not fixed. You start with any instance of vertex cover. But of course, this instance should not be like 4 or 5 vertices, right? Because such an instance is polytime solvable, right? So you, did you want to ask something else or? Okay. So, no. So do you first understand that we are giving reduction from vertex cover to our problem and not the other way? This is okay. So now let me erase this. Let's start, go slow. So what do we want to do from vertex cover? We want to construct instance of CC problem. Okay. In vertex cover, what do I have? A graph G and an integer K. Okay. In CC problem, what do I have? Voters, candidates, rankings. Okay. This is a symbol that rankings for every voter. And yeah, but let me say. And K, committee size. Okay. So given this, I want to construct this such that if this is a yes instance of vertex cover, then if this is a yes, G comma K is a yes instance of vertex cover, if and only if this is a yes instance of CC problem. Okay, this is what we want to do. Okay, okay. Now you have a graph. Okay, so you have a graph, so you have vertices, you have edges. Yeah, so this is how you, yeah, okay. It's not that I will say that, oh, this is the graph, okay. So you can take anything, okay. Whatever is that, your construction of CC will depend on that, okay. But what we do in here, it's a generic reduction, okay. You can start with anything and you will get this, okay. So let's say this is my notation. This is my edge, okay. And U and V are the endpoints of this edge, okay. Now, with respect to this edge, I will construct a voter. Okay. So, my voter is this EUV. This is my voter. Okay. So, with respect to every edge, I have one voter. Okay. With respect to one vertex, I have one candidate. Okay. So, edges goes to voters and vertices goes to candidates. Okay. Okay. So now what are we saying? Look at this edge. Look at its endpoint. Okay. Okay. You will put them here in any order. Okay. And you will put the remaining vertices here in any ordering. Okay. Okay. Now, when I'm constructing this gadget, I will at least try, right, that it captures somehow the vertex cover properties, right? Eventually, I want to prove the equivalence, correct? So I mean, intuitively, it looks like that for every, what? Why? Okay, that's a good question. We should write the decision version here, okay? So K comma eta, let's say, okay? This is my CC score. Okay, so now you are looking for a K-sized committee with CC score at least eta. Okay, that is the thing. Okay, good point. Okay, so this much is clear. Okay, so now what will you do? You want that for every voter, you pick something from here. If somehow I'm able to ensure that, right, then what do I know? For every edge, I have picked one endpoint, right? Correct? Right? This is what we are trying to do. So we will set our eta in a way that you pick something from here, otherwise you will not be able to meet your score. Okay? If you start picking from here, you will not meet your score. Okay? Okay. So now, but what may happen that, okay, fine, I cannot enforce that this will be in the solution, right? All I can say is something from here will be in the solution. Okay? So now here, if you notice, for now I have, let's say, n number of candidates. Correct? Okay. So what is the position of this 1 and 2? Okay. So in eta, what will be the contribution? N minus 1 for every, right? If I pick something from this. So I could say that eta is at least m into n minus 1. Now what is the problem with this? If I say m into n minus 1, this may happen that for someone, you pick this, and then for someone, you are allowed to go here. Correct? So I need to prevent this. Okay. So for this, we will add some one dummy set of candidates. A large set. Okay. And then for some voter, I will add in the opposite direction. Okay. So let's say I have, let's say D1, let's say DJ in some order. I will fix J later. Okay. I have from D1 to DJ. Then for some voter, it is dj to d1. Okay. So now I will just quickly say, because I want to do algorithm, that j, you can, even if you set j is equal to n, j is equal to m, where m is the number of edges, it doesn't work, because again you may say that for someone maybe you can still pick d1 and it is fine, right? So to take care of this issue, what you can do, you can duplicate these voters. Okay. So for every edge, you actually add 2. This is same. You have d1 to dj. Here you do dj to d1. Just reverse it. Okay. And then you will be able to do. Okay. Here you set j is equal to 2m. Okay. So you will be able to do this. You can set n, whatever is this value. Okay. Is the idea clear at least? Okay. If not, the complete reduction. Idea is clear, right? Okay. So now at least you believe that it maybe it is hard. Okay. Okay. So now because you believe, so we cannot hope for polynomial time algorithm, but it doesn't mean that we will just stop thinking about the algorithms, right? So we will try to design some exponential time algorithm. Okay. Okay. So if you notice in this CC, right, every voter is satisfied by one committee member, right? So we can call that as the representative. For this particular voter, this is the representative, right? But voters are like too many, maybe, right? And sorry, candidates are k only, right? So it will happen that for a lot of voters, representative will be same, right? So for example, here, let's take this as blue. This is blue. This is blue. Okay. Okay. So for V1 and V2, representative is this green lady, and for V3, the representative is blue. Correct? Okay. So now you will very soon see the, some matching problem. Okay. So, oh, okay. So let me write here. I don't know where's the slide. So for V1, what is the score of this green lady? 2. For V2, 2. For V3, oops, take this blue. This is blue. 2. Okay. 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 So now once I know this set, right, then what can I do? I can just add one edge, right? And instead of thinking voter wise, I can start thinking set wise, right? So for this set of voters, because the representative is same, right? So I can think of it like, okay, this is what? 4. This is blue. And this is 2. Correct? Now, why am I talking about all this? Because these observations actually give me an algorithm. Okay? Because what is happening here? Let's say I know the partition of voters. Okay? I don't know, but let's say you know, right? That this set of voters, for this set of voters, the representative is same. Suppose you know this. I don't know who is representative, but you know that they are going to have the same representative. That much information, suppose you know. Okay? Okay. So suppose I know that this is going to be the partition of voters. Okay. Okay. Then now you think that, okay, if this particular set is represented by this green lady, then what is going to be the score? Total score. Okay. If they are going to be representative by this red person, then what is going to be the score? And so on and so forth. Does it look too similar to some problem? Right? Maximum weight matching, now you need to find. Okay? Okay. So if you know the partition, right, then you know the problem is, which is polynomial maximum weight matching. Yes? So this is polynomial time solvable, right? But unfortunately, I don't know the partition, right? So if I start, if I try all possible partitions, exactly. Okay, so I can now try all possible partitions. For every partition, find the maximum weight matching, and then at the end, return the one which has the largest weight. Okay, of course, candidate endpoints. Okay, that's going to be your committee. Okay, so this is n to the power n algorithm because you try all possible partitions. Okay, but we can do much better. We can design 2 to the power n algorithm. Okay, okay, I have time now. I'll go slow. Okay, so idea is same, but this partitioning we will not try all possible. We will try to be smart there. Okay, so suppose again let's go over a partition idea once again. You know the partition V1, V2, V3, V4. You know these are the representatives. For V1, C1 is the representative. For V2, C2 is the representative. V3, C3 is the representative. For V4, C4 is the representative, right? And what do I want? This thing. Okay, so I changed the notation here, sorry. But yeah, satisfaction of candidate C1 from the set V1. Okay, this definition is clear to everybody? Okay, this I want greater than or equal to required score, which was eta. Okay. Okay, so we will use the method of polynomial multiplication here. Okay. Okay. So we will try to capture this. Let's say this is a monomial. Okay. Now what is chi here? Okay. So for a set S, let's say now we will use the numbers. Okay. Voters are numbered 1 to n. Okay. Now for S, subset of n, so chi is a n length vector. Okay. Chi S is 1 if sorry. Chi I is 1 if ith bit is in S. 0 otherwise. Okay? You look confused. Is it? Okay. So I will construct this monomial. Okay? Now what is the property of this monomial? You may say that, oh, why am I writing V1 union V2 union V4, right? I mean, I could just write union, right? But the property is that whatever is this set, it can be, it is a union of 4 disjoint sets. Okay, it should be able, we should be able to partition it into 4 disjoint sets, and there exists a subset of candidates C1 to C4 satisfying this property. Okay, okay. So for example, this is my V, right? The whole voter set, right? Then what am I saying? That exponent is union of 4 disjoint sets, right? You have partitioned into 4, and there are 4 candidates such that this is yeah, you satisfy this equation. Is it fine? Everybody? Hmm? Okay. Okay. So, like, this is what we want to do. How will we do? We will come to that. Okay. Okay. So we will start constructing the polynomials. Okay. So for t belongs to n, where n is my number of voters. Okay. So for t belongs to n, and this is my, tell me, this is a maximum possible CC score, right? Right? M is the number of candidates. If you know the eta, you can put eta here. Okay. So this is maximum possible CC score. Okay. So here I will, yes. Yeah, you're right. Correct. This should not be this. This should be m minus 1 into n. Okay. Yeah, you're right. Okay. So the first polynomial says basically it has a monomial y to the power chi x, right? If where x is a subset of Porter set. Okay. If the first thing, this captures the size of the set T. Sorry, wait a second. Sorry. So here, yeah, it's fine. Yeah, this captures the size of the set. Okay. And there exists a candidate such that the satisfaction is alpha. Okay. Okay. So is this definition clear? Right? Okay. So how many such polynomials do you have? I mean T into alpha, right? Right? Okay. Now, so basically T alpha 1 captures that there exists one set, right? Right? Corresponding to which there exists a candidate which meets the whatever the score you are demanding. Right? Now when I'm trying to compute the polynomial PT alpha 2, right? So this superscript basically tells you how many disjoint subsets do you want. Yes. So here you want that you will be looking for total union size is T, right? You want two disjoint subsets and the total score is alpha. Okay. That is why you partition T into two sets T1 and T2, right? Not T two numbers, and alpha also you partition, right? Now from PT1 alpha 1 1, if there is a non-zero, if it's a non-zero polynomial, then what do you know? There exists such a monomial, right? There exists such a monomial, right? And what is the property of that? Let's say this is a yellow one. The property is that the size is T1, correct? Size is T1 and there is a C1 candidate which has the score alpha 1, correct? By definition of PT alpha, you know that for this I have the set yellow and for this set I have the set green, right? But why such a multiplication is not enough? Because they might be overlapping, right? Then of course you are going to just get one representative, right? So either you will get score from C1 or you will get score from C2, correct? So the summation may not give you alpha, correct? So you just want to ensure to get this alpha that these two, you talk about these sets which are disjoint. Now this is the only property which we need to capture here. Are you able to follow what we are trying to do using polynomial multiplication? So far we captured the size, the score, right? Now if we capture that, I will be able to find disjoint sets, then we are done, right? So here we will use the following known result that two sets S1 and S2 are disjoint if and only if the number of ones in the summation of their characteristic vector is same as the size, summation of the size. Okay. Now what will we do? When you multiply these polynomials, their exponent will add up, right? If in this, now after this addition, right, in the exponent, if you have t number of ones, right? If you have t number of ones, then what do you know? These are disjoint, right? Because this size is t1, this size is t2, t1 plus t2 is t, right? And the union also you are saying t. This may only happen if sets are disjoint, correct? So this is, so you will only keep the monomials which have t number of ones in the exponent. Okay. So here, Okay. Okay. So that's all. We are almost done. Okay. So, okay. And now I really do not care if how many such, like, let's say I have y to the power of chi x, right? Now I do not care that how many times does it repeat in your polynomial, right? I only care that it exists, right? So I will forget about the coefficients. Okay? Just ignore the coefficients. If it appears only once, just keep it once. Okay? Okay. So this is what we mean by I mean by R. Okay, just keep the representative. Okay, so ignore the coefficients. And it is important because we are doing polynomial multiplication. So the running time that we want, we need to ignore these coefficients. If the coefficients are large, time complexity will increase. Okay, so this is important also. And we also don't need it. Okay. Okay. So this is how you will compute for 1, 2 up to k. Okay. Okay. And at the end, if for any j, right, n score is non-zero, then you return yes. Okay, you can think of it as like eta. Okay, then you just return yes, otherwise no. Okay. Okay, let's look at the correctness. Okay, so let's say S is a committee with the score eta prime which is greater than or equal to eta. Eta was the desired score. Okay, now I want to claim that you will return yes. Okay, so since it's a there is a solution, right? Now, okay, so when I'm saying x1 to xk is a partition, it's a hypothetical thing. I don't need to construct it. Okay, I know there is a solution, so there is also a partition. This I know. Okay, okay. So I know there's a partition of voters into k sets, right? And you have these representatives, correct? Okay. Now I want to claim that Pn eta prime k has a non-zero term. Okay. So if I prove this, what will you know? When I say n, it means that all the voters are have representative, right? The score is going to be eta prime, and you will get k disjoint subsets, right? Okay. So we will prove it by induction. Okay. So for each j belongs to k, we will just want to prove that. So this x1 xj is the same as the partition induced by solution. Okay. Okay. So we want to say that, well, I mean, if you just look at the picture, that we are not saying anything much. All we are saying is, if you focus on just whatever set you focus on, like whatever is your j, right, then pt alpha j is going to have a monomial, which is the union of these two sets. Right? If j is 2, then these two sets. If j is 3, then x1, x2, x3. You are going to have a monomial which has in the exponent the union of this thing. That's all we want to claim, right? And then inductively we can say that at the end you will have a monomial which will be union of this and has the properties that which are required. Okay? Okay. Okay. So for j is equal to 1, because I know there is a set x1, right, whose representative is c1, right, I know that this will have a monomial y to the power chi x1, correct? When did we start? 2:40. Oh, I thought I had time till 4. Okay, so just five more minutes. So for j is equal to 1, I know that we will be, because I know that there is a set x1 whose representative is c1, right? And this is the satisfaction, right? So for this particular polynomial, I know that I will have a monomial y to the power chi x1, right? All of you already asleep. So for the induction hypothesis, right? Let's say j for j equal to j prime, it is true. I mean, this is a simple induction. For j is equal to j prime plus 1, right? Now look at this particular T, okay, x1 up to xj, okay, and this particular alpha, okay. Now the claim is that pt alpha j prime plus 1, right? When you do this multiplication, you will consider this term, correct? Right? Okay. Where T1 is this, alpha 1 is this, T2 is the remaining, alpha 2 is the remaining. Okay? Okay. Okay. Now, because of the induction hypothesis, what do you know? There exists such a monomial in this polynomial, right? Okay. Because of again induction hypothesis, you know this exists in your T2 alpha 2 1, correct? Now, what do you know? Because it was a solution, you know xj prime plus 1 is disjoint from this, right? So when you will multiply, right, in the exponent, you are going to have a t number of ones, right? Because you already know these are disjoint, right? Because you know this is the solution, right? So this is how you know that you are done. Okay. So reverse direction proof I will leave because we do not have time. But in case you want to discuss, we can discuss during the coffee break. Okay. That's all. Thank you.